Hello and welcome, everyone. My name is Irfan Siddiqui, and it's a pleasure for me to be serving as the current chair of the Department of Physics at the University of California, Berkeley. And it is with great pleasure that I welcome you to the 27th annual J. Robert Oppenheimer Lecture. The Oppenheimer Lecture annual series was established in 1998 and is made possible through the generosity of Jane and Robert Wilson, as well as Steve and Arlene Krieger. The series has brought a who's who of theoretical physics to Berkeley. Past Oppenheimer lecturers have included Mary Gelman, Cian Yang, Freeman Dyson, Helen Quinn, Charlie Kane, Leonard Susskind, Stephen Hawking, Kip Thorne, Lars Bilsten, and our very own Marvin Cohen. The lecturers have come from many fields of physics, including particle physics, condensed matter physics, astrophysics, cosmology, AMO physics, and biophysics. Robert Oppenheimer was born in 1904, growing up in an upper-middle-class family in Manhattan. He graduated from Harvard, majoring in chemistry, and entered Cambridge University in 1924 as a graduate student, hoping to work with Ernest Rutherford. In 1926, Oppenheimer left Cambridge to finish his PhD with Max Born in Göttingen. He published more than a dozen papers while with Born, mostly focused on the new theory at that time of quantum mechanics. This included his most famous work, the Born-Oppenheimer approximation, that simplifies molecular physics by separating slow nuclear motion from faster electron motion. More than 90 years ago, in 1929, after 2 years of postdoctoral study, mostly in Europe, Oppenheimer returned to the United States. He accepted an associate professorship from Berkeley, where he remained for nearly 15 years. During this period, he published his famous paper with Volkoff, establishing the Tolman-Oppenheimer-Volkoff limit on the maximum mass of a neutron star, the mass above which the star must collapse into a black hole. He also developed a theory of that collapse and black hole formation. Both topics are of keen interest today with the most recent observation of gravitational waves from black holes and neutron star mergers. At Berkeley, Oppenheimer cultivated a culture of intellectual rigor amongst his students and colleagues, leading a group of 8 to 10 graduate students and several postdoctoral researchers. He engaged with them daily, a model for all advisors, questioning their progress and pushing the boundaries of theoretical physics. Hans Bethe noted that probably the most important ingredient he brought to his teaching was his exquisite taste. Oppenheimer always knew what were the important problems to work on at any given time. This scientific leadership would later shape not just his career, but also the course of history in 1942. Oppenheimer was chosen to lead the World War II Manhattan Project's engineering lab, sited at Los Alamos, New Mexico, near a ranch which he owned. And under his direction, the Manhattan Project produced the successful test of Trinity. Following World War II, Oppenheimer became a public figure, a symbol of the intersection of science and national policy. He graced the covers of Time and Life magazine, embodying the premise and perils of scientific achievement in the modern world, yet this prominence came at a cost. In 1954, amid the rising fears of the Cold War and McCarthyism, Oppenheimer was stripped of his security clearance in a highly controversial hearing. A decade later, some measure of redemption arrived when President Lyndon Baines Johnson presented Oppenheimer with the nation's Fermi Award, a recognition of his scientific contributions and service to the nation. Oppenheimer's legacy at Berkeley is a simple one, summarized by a plaque on the 4th floor of Physics South with another quote of Hans Bethe. And this one is particularly poignant. In these corner offices, from 1929 to 1942, J. Robert Oppenheimer created the greatest school of theoretical physics the world has ever known, from Hans Bethe. Berkeley Physics strives to continue with this legacy today. Now it is with great pleasure that I introduce Dr. Robert Bergeneau, the Arnold and Barbara Silverman Distinguished Professor of Physics, Material Science and Engineering, and Public Policy, and Chancellor Emeritus of the University of California, Berkeley, to introduce tonight's Oppenheimer Lecture, Dr. Patrick Lee. Professor Bergeneau.
Thank you so much, Irfan. So it's my great pleasure to introduce our distinguished speaker, Dr. Patrick Lee. Professor Lee joined the MIT Physics Department in 1982 after nearly a decade with the Theoretical Physics Department at Bell Laboratories. Patrick and I had been colleagues at Bell Labs 10 years earlier, and I was delighted when we were able to convince him to move to MIT. Manifestly, I was at MIT at the time. He has made key contributions to the theory of disordered electronic systems and is a pioneer in mesoscopic physics, the study of small devices at low temperatures. Professor Lee introduced the concept of universal conductance fluctuations to describe such devices. For this and other contributions, he has received many awards, and I did a fast lookup of them just before the talk. First, in 1991, he was elected to the National Academy of Sciences. In the same year, he won the Oliver E. Buckley Condensed Matter Physics Prize, and the citation was, for his innovative contributions to the theory of electronic properties of solids, especially of strongly interacting and disordered materials. And many of the solid-state physicists who've given this talk before have won this same award. In 2005, he won the Dirac Medal from the International Center for Theoretical Physics for his pioneering contributions to our understanding of disordered and strongly interacting many-body systems. And finally, Patrick, I hadn't heard of this one. I'm particularly fond of this. Just two and a half years ago, in 2022, he won the Anatoly Larkin Senior Research Award of Theoretical Physics from the FTPI for pioneering and wide-reaching research in strongly correlated systems, in particular theories of the quantum transport phenomena in the mesoscopic and superconducting systems, and for his standing in the physics community. And he's the inaugural winner of this new award. Pretty extraordinary. Professor Lee's current research interests focus on the study of strongly correlated electronic systems, such as high-temperature superconductors. In the most interesting cases, the strong interactions between electrons can give rise to novel phenomena that cannot be explained in single electron band structure terms. Examples include the fractional quantum Hall effect, quantum spin liquids, which Professor Lee will discuss today. Quantum spin liquids are exotic phases of matter in which magnetic moments remain in a highly entangled and fluctuating state, even at zero temperature, defying conventional magnetic order. Okay. These systems feature excitations that carry fractional quantum numbers and couple through emergent gauge fields. Their behavior challenges our fundamental understanding of quantum many-body physics and opens up exciting avenues for future exploration and discovery. Experimentalists like myself and James Iniolides spend a lot of our time looking for realizations of quantum spin liquids in real materials, especially in the neighborhood of quantum critical points. Please join me in welcoming Dr. Lee, who will be presenting tonight on emergence of novel particles in quantum magnets. Patrick.
Okay, thank you, Bob, for this great introduction. It's a real pleasure for me to be here. It's a great honor, in fact, to come to the place where theoretical physics and quantum physics really started in the US, to speak in honor of Oppenheimer. As you know, there was a movie about Oppenheimer a few years ago, and Oppenheimer has become a household word. So I was talking to my former student, Charlie Kane, a couple of years ago, and he said, do you know that we are academic descendants of Oppenheimer? I said, no, I didn't know that. How can that be? So I looked it up, and indeed, Charlie was right. So my thesis advisor was Marlin Scully, who was a contemporary of Bob at Yale at the time. His advisor is Lamb. He's a homegrown Berkeley guy, right? Bachelor and PhD. And he won the Nobel Prize in 1955 for the Lamb shift. So he's one of these rare people who can do both theory and experiment. But his famous work is experimental physics. So I didn't imagine that his advisor was Oppenheimer, as this plaque indicated. Okay, so right. So indeed, it's particularly thrilling for me to stand here and give this talk in honor of my long lost great grandfather. Okay. In fact, I will begin my talk with a discussion of the early days of quantum mechanics around this era, where the foundation of solid-state physics, as we know it today, as condensed matter physics, was really set. And that has an influence on everything that we do today. So my title is the emergence of novel phenomenon in quantum magnets, and I will explain whatever single word means there. And let me acknowledge, this is something I've been thinking about for a long time. And let me acknowledge my collaborators, Naoto Nagaosa, Xiaogang Wen, and Sento, and many students and postdocs who have helped my thinking on this subject. So let me go to the beginning. My field is, this thing seems to be dying. My field is condensed matter physics, or quantum materials, which describe the world that we encounter every day. So in fact, the world that we see and touch cannot be understood without quantum mechanics, right? And so I'm going to give you my solid-state physics course in 5 minutes. Right? But you have to pay attention because there will be a quiz. All right. So some of the most fundamental or simple questions we want to ask about solids is that, why are some things metals like a copper wire, and why is something insulated, right? Where do magnets come from? We're all familiar with bar magnet that you put on your refrigerator. Yeah. Where do these things come from? So I claim that we need quantum mechanics to understand all of this. And so quantum is red. So anything that has to do with quantum mechanics, I've colored it in red in the next couple of slides. Okay. So how do we understand solid? Well, solid is an array of nuclei that are arrayed in a periodic way, right? And the electrons are detached from the nuclei and move around. Okay. So this is a very classical concept, and I think it was already understood in the 19th century. Now, the electrons, we know they carry charge and also a spin. It carries a spin 1/2. So for spin, as far as we're concerned, we can think of as just tiny little magnets that are attached to the electrons that can either point up or down. Okay, so that's what spin does. We call it spin 1/2. And so the electrons are supposed to be detached from the nuclei and move around. So this, again, is a very classical idea. By the way, the aficionado may have noticed that this nucleus is displaced from its static position. And this displacement was drawn in honor of Oppenheimer, because Born and Oppenheimer did the famous work of saying that the electrons adiabatically follow this nuclear motion. Yeah, maybe this better. Not much. Maybe I need 2 of them, both of them. And if they are coherent, it will be 4 times as bright, right? So that's quantum mechanics. Right. So I think Berkeley is still in the 20th century because they're green lasers now, right? The locals don't know about green lasers yet. Right. So, where are we? Yeah. So now the important thing that quantum mechanics tells us is that these electrons occupy momentum states. The idea of states is quantum mechanical. And most importantly, electrons are fermions. So we know that there are two kinds of particles, fermions and bosons. And the thing about fermions is that they hate each other. Right? That's the only thing you need to know about fermions. Right? They can't stand each other. So they have to stay apart. They can't occupy the same space or state. Okay? So we call that Pauli exclusion. So these fermions can, each momentum state can accommodate only one electron with a given spin. Right? So that's what quantum mechanics tells us. Well, Felix Bloch, already in 1929, and I was astounded by the date because that's only 4 years after Schrödinger equation, showed us that unlike electron in free space, the electrons in a lattice that's seeing this background nuclei forms what is called an energy band. Right? In free space, the electrons move in a quadratic band. Energy is going like k squared. But in a solid, they form this band in momentum space. And now, by quantum mechanics, each of this band can accommodate just one electron, right, per state. Okay. Now, because there are two spins up and down, so each of this band can accommodate 2 electrons per state. And therefore, if there's an even number of electrons per nuclei, then this lower band will be completely filled, right? And again, Pauli exclusion is very, very important here, because otherwise, if electrons were anything else, they would have collapsed. They would not be filling this state like this. So as a result, this explains why you have insulators, right? Because these electrons are all dead. They're just sitting there. They have no place to go, right? Whereas in a metal, if you have an odd number of electrons per nuclei, then you have what we call a half-fill situation because there are two spins, right? So each band is only half-filled, so that there are a total of 1 electron per unit cell, right? So in that case, only half of these electrons are filled, right? And we call this a gapless situation, and this is what is called a Fermi sea. Right? Fermi sea means that these fill states behave like a puddle or like a sea. They accommodate all the electrons. Okay. Now this is a metal because it costs me nothing to move an electron from this occupied state to an empty state. Right. So that's why we call it a gapless situation. So this thing can carry electricity freely. Okay. So the message here is that you need quantum mechanics to explain the very simple fact that we have metal in insulators. Okay. Yeah. Oops, I got too far. Okay, so here's a summary with the property of metals, the fill Fermi sea. And when we fill the Fermi sea, then we have something called a Fermi surface, which is the last momentum state that is occupied. Right? So there's a shell in 2 dimension, or 3 dimension, there's a shell, which you call Fermi sea. And what are some of the properties of a metal? Well, there's a specific heat. It's linear in temperature. The reason is very simple. Because the electrons in the Fermi sea are mostly dead. Only the ones that are within kT of the Fermi surface have some life, have some entropy. And so immediately you see that specific heat is linear in temperature. The spin susceptibility is constant because the Fermi sea carries spin. And if you apply a magnetic field, the spin up and down are occupied by a different amount, so there's a net a magnetic moment. Electrical conductivity is a constant at low temperature if there are impurity scattering. Okay? And the thermal conductivity, if you plot kappa over T, goes like the conductivity. It's also constant at low temperature. And that's because the extra T is because the electrons are carrying entropy, right, of all the T. And when they move, they carry entropy, and that's why kappa over T. Okay. Well, so the question remains, this is a picture that explains sort of thermodynamic measurement. Are there ways we can detect this Fermi surface and measure its property? right? One of the earliest way is by something called quantum oscillations. And I want to introduce you to this idea. So in the magnetic field, it turns out that this energy dispersion breaks up into discrete states, right? We call them Landau level, okay? And the spacing is proportional to the magnetic field. It's the cyclotron resonance frequency. In the magnetic field, so as you increase the magnetic field, then these levels would move up, right? Because the spacing is increasing. So this discrete state would move up through the Fermi energy, right? And therefore, every time it crosses Fermi energy, something of the property change, right? So therefore, you have some kind of oscillation of the physical property as a function of magnetic field. And it can be any property. It can be conductivity, it can be magnetization, it can be Hall effect, it can be anything, right? So the general formula is given by some sinusoidal function. A is the area of the Fermi surface that you have up here. And now it turns out that this B, in fact, it sees a projection of B along the, if you have a two-dimensional electron gas, it sees the magnetic field perpendicular to the plane, so cosine theta. And so this is the formula. And so now, if you measure this from the period in 1 over B, then you can extract the Fermi surface area. Okay? So this was used for large effects in the 60s to measure Fermi surface. And I happen to have some data. And this happens to be on high-temperature superconductors. Okay? And it's a little bit unusual because you need to apply an enormous magnetic field, like 20 Tesla, to kill the superconductor. But beyond that, you can start seeing oscillations in the, what's called magnetization torque. That's because they have a very sensitive way of measuring the magnetization by the torque measurement. Okay? Now, this doesn't look periodic in B, right? You see that the period is increasing. But if you plot it versus 1 over B, you can see that's nice periodic, right? And then from the period, you can infer the area. Right? So it's a very powerful way of using quantum mechanics to determine the size of the Fermi surface. Right? Okay. Right. So that's the history. The message I want to tell you today is that all these properties, except for the electrical conductivity, are seen in something which I call emergent neutral fermions. So I claim that in condensed matter physics, it's possible to find a situation where in low temperature, some totally new particles emerge that was not there in nature in the short distance scale, right? And the way we detect it is by doing exactly the same kind of experiments we use to detect electrons, okay? So that would be my main message for today. So if you want to fall asleep from now, it's fine. But just wake up for my quiz. Okay, now let's see what my timing is. Okay, that's fine. All right. Okay, so just one more advertisement for my field. What do I like about my field? Why is it so interesting to me? It's a very nice field to work because there's a close relationship between theory and experiment. I don't have to wait 40 years for someone to build an enormous machine to test my ideas, right? I can go down this corridor, talk to my friends, and they will quickly show whether I'm right or wrong. And if I'm lucky, I get to publish my paper before they show that it's wrong. So, yeah, but it's very nice to have this back and forth. And I like to see this as a kind of a free ring circus. There's theory, you need samples, and you need someone to measure to the measurement. If you're missing any one of these components, these rings fall apart, right? And so, and this synergism that drives our field will be evident in the examples that I will show you today. Okay, so what I'm going to tell you is very much the collaboration between theory and experiment and sample growers. We need all these components to make progress in this field. Because it's a difficult field, it's a complicated subject, and none of us can do this on its own. Okay, so now you're asking, what is new? Okay? why am I here? Okay, so the basic idea is this notion of emergence in condensed matter physics. So I think I mentioned it before. I want to have low energy excitations. So in physics, quantum physics tells us that there's a ground state, which can be rather complicated, but the physical properties are not controlled by the ground state. We don't care what the ground state is doing. It's controlled by the excitation, right? It's only the excitations that we can see, right? The ground state is just a dead object. So the excitations are generally particles or fields. Okay, so these things, the claim is that they can emerge at low temperature. If you cool down to low temperature or low energy, they are not in the original matter, right? Because in solid-state physics, the original matter is just made up of electrons and nuclei. We don't do elementary particles physics, so we don't look inside the nuclei. So everything is just basically electrons and some heavy nuclei, right? And now also remember that the electrons are fermions. They carry charge and spin, right? They carry both things. So I think the best characterized example of emergence comes with this fractional quantum Hall effect. And in that case, there are fractionally charged particles that emerge, right? We know the electrons have charge E, but these quasi-particles that emerge carry charge 1/3, 1/5, and so on and so forth. Very surprising. And this is responsible for the fractional quantum Hall effects. And have been directly verified by experiments. People can measure shot noise and see that there are particles that are carrying less than 1 unit charge. Okay. Now that's a well understood. I'm not going to discuss it today. I will talk about it in a different place where these emergence may happen, and that is that in certain quantum magnets, a new state of matter called a quantum spin liquid may show up as a ground state, which can support excitations, which can carry spin but no charge. Okay, so this is as if the electrons has lost its charge, but it still retains its spin. Okay, and it retains being a fermion. Okay, so we call it spinons. And in that case, then you can imagine all kinds of experiments you can try to do to detect it. Right? Okay, so I will explain how this comes about and show evidence that this may be true in certain materials. Okay, so I still have to go back to my solid-state physics course to explain magnetism. I explained metal and insulator. I didn't talk about magnetism. So where does magnetism come from? Okay. Well, it turns out that I lied to you a little bit, as all teachers have to at some point. I said that when you have 1 electron per site, the system should be a metal, according to band theory. But in reality, there are many materials which are insulator, even if they have 1 electron per unit cell, per site. And that is because of Coulomb repulsion. But the band theory I told you about did not take into account the interaction of the electron with each other. Okay. And that was recognized by Mott, again, very early on in the 1930s. And so the idea is as following. I have 1 electron per site. So just pay attention to the red balls for now. Forget about the orange, the yellow ball. Now, 1 electron per site means that each site can accommodate only 1 electron, okay? And say they're sitting there. So the charge degrees of freedom is frozen, right? Because there's strong repulsion, so this electron would cost it energy to go to the neighbor, right? There's some Coulomb energy to put 2 electrons on the same site, right? Right. So that's why we have an insulator, because the electrons cannot move, right? In order to move, it has to doubly occupy the site, and it costs it energy, which it doesn't like. Okay. So this is a different kind of insulator. We call it a Mott insulator. It's a different kind of insulator because it violates the band theory that I was telling you about. Okay. Because due to interaction. Okay. Now, notice I've drawn this in the spin. See, the charge degrees of freedom is dead, but it still has a spin, right? So the spin degrees of freedom is still alive, right? We remember the little magnet can point either up or down. Okay? So I've drawn it in a special way, which is a up and down array, which we call an antiferromagnet. In other words, each up spin is surrounded by down spin. In this case, right? A ferromagnet would have every spin parallel. Okay. So that was understood. Oops. We call it a Heisenberg model. The reason that's the case is that there is a interaction that favors the spins to be antiferromagnetic aligned. Right? It obeys this Heisenberg Hamiltonian. The reason is very simple. If I start with this configuration, I can take this electron and virtually move it to the neighbor and come back, right? And that's again quantum mechanics. I can virtually make transition. Then that virtual transition gave me an energy, which is T squared over U. T is a hopping energy and U is the energy denominator, right? And second order perturbation theory is always attractive. So this term tends to gain me energy. Right? On the other hand, if the spins are parallel to each other, even this path is forbidden. And it's strictly forbidden by Pauli exclusion, because the parallel spins cannot occupy the same site, no matter what. Right? And here, the opposite spins, they don't like each other, but they don't hate each other as much as the parallel spin does. Right? So they can still gain a little bit of energy. Right? So we have this Heisenberg exchange. Right? So we know that the spins like to align anti-parallel with each other. Then Néel then says that, well, if that's the case, then the ground state should be an ordered state where the spins are lined up like this. So this is called antiferromagnetic state. Okay? And that was proposed in 1936, for which he got the Nobel Prize in 1970. All right, so now, today we're so jaded in our understanding, it's so commonplace that antiferromagnetic, that one might reasonably ask, is this a kind of obvious idea? Why is it deserving of a Nobel Prize? Right? It's pretty obvious, right? Is that true, right? It's obvious, right? Yes. Okay, so you can do something obvious and still win a Nobel Prize. That's message number one. Well, I looked into the history a little bit. Turns out that it's not as obvious as I thought. Okay. What I learned is there was an obituary written by Jacques Friedel for Néel in Physics Today, 2001. So he said that, okay, so Néel developed this concept of antiferromagnetism, but he was attacked. The people didn't believe him. No less than famous people like Landau. Okay. So Friedel report that Landau suggests that quantum fluctuation would mix Néel's solution with that obtained by reversing the moments. So Néel's solution is we have spin up and down, spin up and down. Now the Heisenberg model allows you to have a mutual spin flip. Then up and down can flip with each other. That is called quantum fluctuation, right? So if you act on Néel's state with a Hamiltonian, with the Heisenberg Hamiltonian, it will generate this spin flip, right? So from that we know that the Néel state is not an exact eigenstate of the Heisenberg Hamiltonian. Unlike the ferromagnet is an exact eigenstate, quantum mechanically exact eigenstate. Okay? So he has reason to doubt that Néel is right. He says that quantum fluctuation will kill the state. Okay? And that was because it's not accurate enough. Right? So that was in the 1930s. You know, so it's kind of Néel was kind of like the classics. Néel's argument is entirely classical. But people were thinking very much quantum mechanics at that time. Okay? And so Friedel went on to write that Néel's difficulty with antiferromagnetism, an inconclusive discussion in the Strasbourg International Meeting in 1939, fostered his skepticism about the usefulness of quantum mechanics. This was one of the few limitations of this superior mind. So apparently, if you have a run-in with Landau, it can cause permanent damage to you. So I think with this suffering, Néel did deserve his Nobel Prize. Okay, so if I cast this in maybe more modern language, I will start with this. Suppose I start with two spins. spin and a half. Then we know that the ground state is what we call a spin singlet, which is a superposition of up, down, and down, up, right? And nowadays it's called a bell pair, or and so on and so forth, right? But so I'm going to denote this singlet by oblong, by a blue oblong. It's always going to be blue. Okay. Now, so quantum mechanics tells you that you can at mixed state, right? Superposition of states. So it's another trademark of quantum mechanics. Now, the energy of this state equals, that's a homework problem, I guess, S times S plus 1, right? And if you work it out, put 1/2 there, you find that you can gain 3/4 of J per singlet, right? Which is 3/8 per spin. In an AL state, if you simply have up and down, what you can gain is 1/4, because it's 1/2 times a half, right? So, therefore, 3/8 is better than 1/4, right? So this singlet is better than than the classical state. And you can see that this is quantum mechanics because you have to go to very large S. If you go to large S, then you can ignore the 1, then you get back the classical result. So 1 is quantum mechanics. Okay? So the quantum is what makes a difference. So as an example, if we take a one-dimensional chain, Néel would say that the ground state should be up, down, up, down, up, down. But I can just make a bunch of singlets, and this, by this argument, would already have lower energy than the Néel state. If I further improve this by making superposition, quantum mechanical position, then I can gain even further. Okay. And amazingly, that was already understood by Hans Bethe in 1933, when he managed to solve exactly the spin chain solution, and this solution can be understood as a superposition of singlets. Okay, so now we see that in 1D, Néel was definitely wrong. Okay, in higher dimension, he would win because in higher dimension, each site have many more neighbors, right? And so you can gain per neighbor, but if you make singlet covering, you can only gain so much per spin, right? So if you go to 3D, Néel wins, right? So the natural question is that what happens in between? What happens in 2D, right? Is there a competition? So that's the basis of Phil Anderson's famous paper in 1973. So he asked the question, is there a place where in 2D, in 2 dimension, we can show that Néel is wrong? That the ground state is not in Néel's ordered state, but something else. Okay? And his starting point is to say that the place to look for this is a triangular lattice. A triangular lattice has a property that of frustration. So frustration means that if this is spin up and this is spin down, spin up, spin down. If you're here, the spin doesn't know which way to turn, right? Because it's always seeing 2 neighbors that are giving him opposite signals, right? So therefore, this is very unfavorable to the Néel state because you have this frustration. So he said, let's look there, and maybe we have a chance of overcoming Néel, right? So he proposed that instead of the Néel state, very classical state, to form a thing out of this singlet state that I was telling you about, which is a quantum mechanical superposition of the states. So these are the dimers, these are the blue things, and they can cover the triangular lattice, right? But there are many ways to cover the triangular lattice, right? And we have quantum mechanics, so why don't we just make a linear superposition of all possible covering, right? And that would be his picture of the spin liquid. So he calls this a resonating valence bond, or RVP. Okay. Now we can generalize this instead of just nearest neighbor singlet. We can make longer singlet, arbitrary long singlet pairs, and so on. Okay. So that's the starting of the beginning of the spin liquid idea. That's what I'm doing. Okay. I have to rush through my course a little faster. Right. So now we have the ground state. Let's ask ourselves, what about excitations? Right? In an AL state, the classical state, the excitation is that we take a spin and flip it. Right? So that is actually a spin 1 excitation because we took it down and end up with a 1. So that's a spin 1 excitation. And similarly, if I have a frozen dimer, if I take a singlet and flip one spin, that's a triplet excitation. So that's a spin 1 excitation. Okay? Yeah. But the idea is that in the spin liquid ground state, it is possible to have a spin half excitation. Okay? And these can be fermions as opposed to boson, which is the ordinary spin 1 excitation. Now, how is that possible? Well, I can kind of give you an idea by showing these pictures. So suppose I take a single dimer and flip the spin, right? So I have two spin up guys, right? I'm going to show you that these two guys can now move apart from each other, okay? And if I can separate them without costing me much energy, then I have to make two individual spin half excitations out of the spin 1. Right? So we can say that the spin 1 has fractionalized into two spin and a half excitations. Okay? Now how does this work? Well, that's illustrated here. Suppose I remove this and let me forget about this guy for a minute and look at this guy. You can see that this one can go to the change the position if I'm allowing this dimer to go from here to here. Right? I can locally, with everybody else is fixed. This spin can go here if the dimer moves from here to here. Right? Is that clear? Right? So it's just involving a flip of one dimer. Now, that's ordinary. If you have a frozen dimers configuration, that's not possible because everything is frozen. But if I have a superposition of all these covering, then there's a transition matrix between these two. Okay, so that's the game where quantum mechanics comes in. Right? So this linear superposition is very important. In modern language, they would call this a highly entangled system. Okay, but but we've been dealing with highly entangled system all our lives, right? So it's nothing surprising. Right. So this is how pictorially you can go from a spin 1 to fractionalize into 2 spin and a half. Okay, is that clear? That this is one of the key. It's just my picture, so it's not quite true. That, we all have to lie at some point. Okay. So if you don't lie, you make a formal description, and it's a series of compact gauge field coupled to fermions, and we have a phenomenon called confinement, right? That's known from QCD. So the enemy of the spin liquid is confinement. So for example, I showed you this picture of the electrons, right? So the electrons carry spin and a charge. This would be a metal if the spin charge are running around, or it can be a mod insulator if they both confine to the nuclei. So what the spin liquid does is that you can imagine breaking this electron into two pieces, and you put the charge to be next to the nucleus to localize it, but the spin nucleus of radium is left free to run around. Right? So this is how you can get this neutral fermion out of electron, and they can run around. Okay, picture. So turns out that if formalism allows you to do that, so the message is that these particles are emergent particles because, in nature, our starting point, we don't have any such neutral fermions. Right? They emerge as a consequence of this strong correlation. And furthermore, these interact strongly with something called gauge field. Just like the electrons in our world interact with electromagnetic field, which is a gauge field. Okay? So there's a one-to-one correspondence between the two, which I'll take advantage of later. Okay. Well, this sounds crazy, right? And indeed, just like Nael had, these ideas were initially met with a lot of skepticism, okay? Except it's going the opposite way, because now it is, you're fighting against the old guards, always fighting against the old guards, right? Yeah, but now we have exact solution, mainly due to Kitaev, who have a concrete model which you can solve exactly, that show exactly this phenomenon of some emergent particles and fields at low energy. So I think the existence of this spin liquid state is no longer in doubt, in theory. So the remaining question is that, can we see them in the experiment? Yeah, so one more thing I have to tell you, and I focused on the particles, the neutral particles, which is the neutral fermion. I also talk about gauge field. So I said that this neutral fermion is seeing some gauge field. What is the physical manifestation of this gauge field? Can I describe it in terms of spin? Because my only low energy degree is freedom of spin. Right? My charge is gone. It's locked out. Well, it turns out that if you take spins on the plaquette, and they have some frozen, if I take an instant snapshot, I would see a picture like this. Right? If I take an electron and move a particle and move it around, a particle carrying a spin and move it around this plaquette, it's going to see what is called a Berry's phase, because locally, the electron is going to line up with the quantization axis, but the quantization axis is meandering as I go around. So that picks up a quantum mechanical phase called Berry's phase, and that plays a role of a magnetic field. Okay? So the magnetic flux, this is the origin of the magnetic flux that is seen by the fermion. But in physical terms, it turns out that this flux is proportional to something called the scalar chirality, which is a S1 dot S2 cross S3, which basically is the area subtended by these free spin. So these have to be non-collinear spin. If a spin has a non-collinear situation, then we have this magnetic field. Okay. So now I have all the pieces I need to tell you the story. Why is this interesting? Well, I don't need to bore you with this. It is interesting. How do we detect these particles, right? So there are many forms of spin liquid. Some are gapped, some are gapless. For this talk, I'm going to focus on gapless spin liquid because the gap versions are kind of featureless. So it's very hard to tell that they are there and distinguish it from other phenomena. But the gapless one, as I will show you, and I already showed you, they have very definite signatures that we can look for in experiment. So it's more promising. Now, where to look for spin liquid? And here, I'm just going to give you a laundry list of where people have tried over the last 30 years with varying degree of success. And notice the large variety of materials. So this is where the material scientist comes in. People have to know how to make materials of different kinds. Organics, inorganic, and so on and so forth. So the first one that was prominent was using this frustration idea. Right? And the most frustrated lattice is called a kagome lattice. So I'm going to return and talk about this in much greater detail in 2 minutes. So we'll leave that alone. And then there are other things that are not as promising, but I won't go into that. No. Yeah. There's a second route to search for the spin liquid, and that is to be near a Mott insulator. Remember I told you that this funny insulator where the spins are localized, but there will be a transition. As I change the amount of interaction, there will be a transition from an insulating state to a metallic state, right? Near there is a good place to look for the spin liquid, right? Because near there, the electrons don't know whether it's going to be, wants to be a metal or an insulator. They get confused, right? So we make our living off things that are confused, right? So that's a good place to look. And I think the organics is something that has been studied, and that's the most promising place. Let me just quickly, because I'm running out of time, it satisfies the following thing. It has a specific heat, which goes to a constant, so it's linear. Remember, the electrons has a specific heat that goes linear in temperature. This is an insulator, but it behaves like a metal as far as the specific heat and the spin susceptibility is concerned. Okay, thermal conductivity has been measured, but it's controversial. And quantum oscillations, I've talked about, has been searched for, but not been found. Okay. So in the last remaining, maybe I still have 10 minutes. Yeah, let me use 10 minutes. I want to tell you some very exciting recent development, and that's going back to this kagome system. Okay, the kagome is a name of a Japanese name for a basket. Okay, and you can find this very common. You notice this basket is mostly holes, right? So it's the most economical way to make a basket. And the lattice structure is this. If you cut a piece of this, it looks like a Star of David. The unit cell is this. So it's made up of one up triangle, one down triangle, and then hexagon. Right. So that's the structure of a kagome lattice. Okay. It's considered the most frustrated of the two-dimensional lattice because the triangles are sharing points, right? They're sharing corner instead of sharing edges. Right? The triangular lattice, they share edge, so they can still communicate with each other. So these guys, the triangles are really not communicating with each other very well. So theory predicts that in the Heisenberg model, this thing very likely would have something like a quantum spin liquid. Okay? So since we're talking about genealogy, let me give you the genealogy of the quantum kagome compound with spin and a half, because the other criterion is that we want the most quantum mechanical things, right? So we want the lowest spin possible. So we want spin and a half because large spin becomes too classical for this quantum fluctuation to work. Right? So that's what we're looking for. The first popular example was something called herbert-smithite, which is actually a naturally occurring mineral. But a chemist at MIT, Nocera, managed to purify this and work with my colleague Young Lee, former student of Bob. And they were famous to do the first work on this thing. To me, it's absolutely amazing that nature would actually conspire to build such a lattice, right? A perfect lattice that looks like a basket, right? Right. Unfortunately, this thing has zinc and copper. The active material is copper. So what you have is a copper sitting on these kagome sites. The copper is carried spin and a half. Okay, but there's zinc in the layer next by, and zinc and copper are neighbors on the periodic table, right? Some theoretical physicists may not know that, but it's true. And they have almost the same ionic radius, right? So they can trade places with each other. So the trouble is that some copper entered this zinc position and form what we call an orphan spin, right? They're local moments, so they end up dominating the low energy spin fluctuation, and obscure the physics of if there's an kagome or not. Right? So that's the tragedy of this system. Okay, yeah. So the next phase of this is in 2016. Some chemists in China figure out to make a closely related material where they replace the zinc by yttrium. Okay? Yttrium has a very different ionic radius than zinc. So this replacement does not take place. So they solved this problem, right? So they managed to make a perfect kagome lattice, right? Is that cause for celebration? No. The system turns out to order. Neil was right. The system, you make a perfect kagome lattice and it orders antiferromagnetically. Okay? Well, that was unfortunate fact was actually predicted by theory, because this system is not purely describable by Heisenberg model. There's something called the Jaroszewski-Moria term, which is a cross product. So instead of being with two spins, you can either make a dot product or a cross product, right? So you can make a cross product, and this cross product tells you that the spins want to have an angle between them, right? And so that thing favors this 120 degrees phase, because there's a canting angle between them. And theory have already shown that a very tiny amount of Jaroszewski-Moria term would destroy the spin liquid and lead to this ordered state. Okay? So the experimentalists was unhappy, the theorists were happy, but no, that's not very good. So the next phase is that people didn't give up, fortunately. So they started substituting chlorine with bromine. Notice that the structure is basically identical as far as the kagome is concerned. And, but it turns out that to make these materials, they are made in this so-called they're made in water. You have to cook this in water. And so you cannot control the amount of OH that goes in and out of your sample. So sometimes some OH goes in, and when enough of them goes in, then indeed, then you kill the disorder. You kill the nail state, and you end up with a disorder state, which is the first step towards saying that you have a spin liquid. Okay, so you still pay a price. Instead of this local moment, you have some disorder in the exchange coupling now, because this thing turns out that you have some kind of a distribution of exchange. But at least you get to where you want the spin liquid. So the situation is a little bit in flux. When I looked at it, I thought the data looks very interesting, but it's hard to tell what's going on. So I talked to my friend Lu Li and said, this is interesting. Maybe we should take a look at it. And we got some sample from Xilang Li's group in China. And Lu Li said, I happen to have some time at the Magnet Lab in a few weeks. Why don't we take this sample and take it there and measure, right? So that was a very lucky thing that he did, because the first thing he discovered is, notice he took this up to 70 Tesla, which is a pulse field measurement. The highest field you can get in the lab is like 17, 18 Tesla. So at the Magnet Lab, you can get pulse field measurement. And the first thing he discovered is that this magnetization plateau. This is a magnetization versus magnetic field. There's a plateau at 1/3 and the one at 1/9. The 1/3 one is trivial because there's 3 coppers per unit cell, per this kagome cell. And if you fully align one of them and the other, say, form a singlet, then you have a plateau. 1/9 is not trivial. Okay, so that tells you that there's something very interesting maybe going on. So in terms of this spinon language, to get 1/9 plateau, you need to have 9 bands. Right? In any fermionic language, to get plateau, you need 9 bands, so you can fill up 5 of them with upspin and 4 of them with downspin. Right? So the net one is 1 out of 9 is polarized. That's how you get a plateau. Right? Now, don't ask me where this 9 bands come from. I'll come back and discuss it later. Okay, but that's what you need. Right? So this is, in fact, band number 4, number 5. So if your chemical potential is for the upspin is here, then you have this thing. Now, so these are high field experiments. If you look at this in greater detail, you notice that this thing looks like a V. Right? If it's a fully gapped situation, you should expect a U-shaped thing because it's gapped. This is a V-shape. So this suggests a kind of a gapless Dirac spectrum. Gapless Dirac spectrum simply means that this gap has collapsed and touched each other in this way, just like graphene. Okay. But the most remarkable thing they discover is some oscillation. So if they do very accurate measurement, they see that the magnetization has an oscillatory feature right near this 1/9 plateau. Right? It's associated with 1/9 plateau. They don't see it anywhere else. Okay? And you see this oscillation. And these data for different angles relative to the z-axis. So as a function of angle, this oscillation changes the period, changes the shape in a rather complicated way. Okay? So that's a great discovery. Okay, so here's a quiz. What does this remind you of, this oscillation? Right? That's the quantum oscillation I showed you earlier. Right? And magnetization has some oscillation. Of course, they see many more periods. You only see, okay, on a good day, maybe 3 or 4, maybe 3, right? But something similar. And but this is very mysterious because magnetization in quantum oscillation are seen only in metals. We need metals, a Fermi surface, and we need this lambda level to move through. Right? This guy is a very robust insulator. It's a 3 eV gap. It's a very strong insulator. There are no electrons anywhere. So how can we say that this is related, right? Okay. So you should not believe me. Right? In fact, I don't think you do. There are two problems with this story, right? One is that the spinons are charged. I spent a lot of effort telling you that the spinons are charged. So how did they see the magnetic field? Why would they be sensitive to magnetic field? Okay? Okay, I have an answer to every question. Okay? So the answer is that the external field actually induces this gauge magnetic field that I told you about. And the spinon sees a gauge magnetic field. Okay, I'll explain that a little later. The second problem is that this oscillation is not periodic in 1 over p. See, here you can completely see that the period is increasing as I increase p. This is not so. Okay? So we need some ingenuity. So it turns out that, so this is a conventional quantum oscillation is described by this formula that I showed before. It's 1 over b cosine theta and the Fermi surface. So the claim is that if I assume that the spectrum for the spinon is a Dirac-like spectrum, then I have a chance of explaining this. Why is that? Because the magnetic field plays two roles. The first role is that is a Zeeman energy, right? The magnetic field carries Zeeman. So it changes the chemical potential of the electron. It moves it up, right? And that creates a Fermi surface. Right? At the Dirac point, there's no Fermi surface. But once I deviate from this 1,9 plateau, I see a fine Fermi surface. And the Fermi surface area goes like B minus B naught squared. Right? B naught is the point of the 1,9 plateau, right? Because it goes like the square of this radius. And you might add to that the conventional picture that the other side is that the orbital part of the magnetic field, you see the CS's component of the magnetic field here. So I can have this formula, right? So with this one simple formula, it turns out that you can fit all the data as a function of angle. So this is only half of the data they measured. All these plots. Anyway, and there are only 3 parameters. The B naught, which should be a constant, and the delta B, which you expect to go like cosine theta, because you should see the projection onto the c-axis. And so this is the delta B that we extract, and the solid line is a cosine theta. So it works pretty well, and the B is kind of constant, right? So I want to emphasize that with one simple formula, you can fit a lot of data. Furthermore, more recently, they measured the specific heat in this thing. So the specific heat over T, C over T has a linear term. Okay, that's what you expect for a Dirac spectrum, right? Specific heat. For Fermi surface, it should go to a constant. So in fact, it looks like there is a constant piece, but there's also a linear piece. And you can now go back to the magnetization measurement, the susceptibility measurement, and plot the low temperature part. It also has a linear piece. If you take the ratio of these two, form what is called Wilson ratio, you get a number which is like 0.5, which is close enough to 1 that you think that they are reflecting the same phenomenon. Okay. So the final questions, these are my final 2 slides. Where does the gauge magnetic field come from, right? Because where does it come from? Well, so we explained this in the paper with the postdoc, Yuming Kang. And it goes back to this Jaroszynski-Moria term that I was telling you about, right? There was this Jaroszynski-Moria term, so that if this term is present, then the cross product is non-zero, right? In fact, it should be the Z component of this cross product is not zero. Now remember, the magnetic flux is proportional to the scalar chirality. So I can just factorize this into 2 pieces. This is non-zero due to Jaroszynski-Moria. This is non-zero because I have a magnetization plateau. Right? So this is non-zero. Right? So this way I can get a magnetic gauge flux which is proportional to B. Okay? And we can estimate the size. The second term is that is there a more microscopic model for where this Dirac band comes from? Up to now, I've just assumed that they're there to fit the data. But it turns out that you can make a microscopic model, and that's where this 9 band comes from. So with 9 bands, how do you get 9 bands? One way is to triple the unit cell, but we don't want to do that, right? Because there's no phase transition that is seen. If you don't do that, the only way I know is to create what's called a 2 pi over 3 flux phase. In other words, I put a flux, 1 flux over 3 unit cell. That doesn't destroy the translational symmetry, but it does make 9 bands, right? Because as far as the gauge field is concerned, it's seeing triple in itself, okay? And we suggested this, and the group did the calculation with projected Monte Carlo method, and surprisingly, they found a very good energy with this trial wave function, which sounds crazy at first, right? So that's a kind of microscopic origin of this phenomenon. Now, if you have to do this in the presence of a magnetic field near the plateau, near the 1,9 plateau, then you find that this state actually it works very well. However, this state has a gap. Well, here again, the DM, the gyroscopic term, comes to a rescue. If you include the gyroscopic term, we show that this gap actually closes as you turn on the field. So the gap closes, and in fact, there's a mechanism for it to stay close before it reopens. That's a little bit more complicated. So I think we have a microscopic picture that may explain why this thing is happening. Okay, so I think there's very good evidence that we actually now have fermionic spinons in this thing which we call Y-cope. The specific heat and the susceptibility is not gap, is not, at least there's some low energy excitations there. There's quantum oscillations. We have not, the thermal conductivity has to be measured at 25 Tesla, so that's difficult, but they're trying it. It's in progress. So the conclusion is that I think quantum mechanics, this quantum spin liquid is a new example of this phenomenon of emergence. And I think this, well, if anything else, it's a good example of how collaboration between sample growers, experimenters, and theorists together lead us to progress in this field. And I'm confident there will be a lot more to come. Thank you very much.
For a wonderful talk. The presentation is open to questions from the audience.
Hi, thank you for the talk. This is a bit of a weird question. I found a paper that suggests for spectral evidence for Dirac spinons, basically using the same ytterbium molecule that you listed, but with, what is it? Yeah, with deuterium replacing the hydrogen in the OH.
Right.
Why? Could you maybe explain? I don't know. This is weird.
Yeah. So there's as I said, there's a history of this. This compound has been around for a few years, about 3 years, and mainly studied in China by 2 groups. And the work is at low magnetic field. And my feeling about the low magnetic, and they show very interesting results. There's a linear specific heat, C over T specific heat that depends on field and so on. But there's something that's not right because the spin susceptibility goes to constant. So it's inconsistent with this Dirac picture. In fact, that was my original motivation to approach Lu Li. I said that, well, if you have a very sensitive magnetometer, maybe we can sort this out. Okay? So I think the situation there is not clear at low field. My hope is that with this very high field, that the problems with the low field may be cleared up somehow, right? Maybe it's less sensitive to disorder or whatever effect. We don't understand. The modeling we did so far do not take into account the disorder. We know that there's some random exchange. So yeah, there are many open questions. I think at low field, there is another compound, which is the Y-capelacite, studied by a French group. It orders at very low temperature, at 2 degrees. And the physical property looks very much like this thing. So I don't know whether that, maybe this thing at low field is just a disordered version of some poorly ordered magnet. So I think the low field is open. So we're very lucky to get into this very high field regime. I'm hoping that this is a new state. So our thinking is that this high field state is actually a different state from the low field state.
Hi. Thank you so much for the talk. I had a question regarding spin-ons. So you said, so if you have a nucleus and then when you have an electron, the charge can go to like get attached to the nucleus or something, and you can have a particle with no charge but spin.
Right.
And I think you mentioned that's not exactly how it happens or something. So could you explain what exactly is happening? Or if you could try, or do we know?
Well, it does happen. It exactly what happens. What I meant is that I cannot show you in detail how it happened, right? Not by the pictures. I just give you a guide.
So,
Okay, so
what happens to the charge exactly then? Yeah, could you just explain what happened?
yeah, so I think you got the story right? So the charge, so somehow the charge is attached to the nucleus, and it cannot move. It's stuck there, but the spin degrees of freedom is still alive, right? So normally, if you have this situation, the spin can just flip, and you have a spin 1 excitation, right? So the magic is that you can take the spin 1 excitation and separate it into 2 spin and a half. So that's where the magic comes. Okay. And I tried to illustrate that magic with this picture of this dimers, jumping around. That's not a proof, right? So that's what I mean that I did not show you completely the story. And I think you're right. I mean, a large fraction of the community did not believe that this is true, that this can happen. There are papers published in physical review letters that said that this cannot happen. But I think Kitaev was my hero, that he actually has a model, and he solved it exactly. And the outcome is not exactly, it's something a little bit different, but it has the same feature, that new particles and new field showed up.
Okay, thank you so much.
Hello, thank you. I was just wondering why does this search for conductivity have to happen at like the 25 Tesla? And like what does that look like, the search for the conductivity?
0.5 Tesla.
Oh, 0.5, so, okay, sorry. Do I repeat the question?
They search for thermal conductivity.
Yeah, The last thing that is still has
the
a
thermal
question mark.
conductivity.
Yeah.
This has to be done at the magnet lab. It's not easy to do, because this phenomenon happens at 25 Tesla.
Okay.
You see, in the lab you don't have a 25 Tesla magnet, so you have to get time. So it's a matter of time. Yeah, I think they have the technique to do it. You have to deal with applying for time in the magnet, and so you wait and so on. Yeah, but I think it will get done.
Yeah, I was wondering like why does it have to be at that super high magnetic field?
Oh yeah,
strength?
because that's related to my answer to the earlier question. I think the state that shows up happens only at 20 Tesla. It's different from this low magnetic field state. A low magnetic field, something else has happening, and it's also mysterious. It's not understood, right? But I think we understand better. We have a chance to understand better what happens at 20 Tesla, because it fills in all the boxes, right? Checked all the boxes. Right? So the thermal conductivity, the interest of that experiment is that it tells you whether these objects are mobile or not. The thermodynamic measurement doesn't tell you whether these objects are stationary, are they localized, and so on, right? So that's why the thermal conductivity is an interesting measurement.
So I wanted to ask a question also, if possible. So you had mentioned this route of synthesizing materials with some particular properties, and of course it's challenging because you may have other terms that are there.
Right.
There is this emerging capability of quantum simulators, whether one uses Rydberg atoms or superconducting qubits, etc. And of course, it's challenging to simulate fermions because you're perhaps doing a Jordan-Wigner transformation or Ravi and Kitaev. Is there some methodology to simulate this kind of charge-free spin-on type of excitation?
Yeah, well, there are people are working on it. In fact, I think there was some work out of the Harvard group of Misha Lukin, right? That has a related flavor to this that Ashwin from here, who used to be here, worked on. So there is some hope of making some progress there. But as you said, cooling. So these are very low temperature phenomena, You have to get to a temperature scale which is much less than the exchange scale. Right? In this experiment, in this material, the exchange scale is 50 Kelvin. And this thing shows up at below 1 Kelvin. Right? So you have to be 50 to 100 times below the exchange scale. So I think it will be very difficult for the go-atom people to get there. But they have other tricks. I cannot underestimate. These are clever people. So, but they're making some progress on this kind of dimer model.
Sorry, I think the mic just kicked in. Thank you for the talk. So my question was actually about temperature. So I saw the plot that you showed earlier. The data was taken around like 400 millikelvin. And naively, can you comment a bit about how this phenomenon evolves as you go lower in temperature? Do you get freeze out at some point, or is that something that's yet to be explored?
Yeah, unfortunately, currently the experiment cannot go below 0.4 Kelvin. But there should not be any freeze-out phenomenon, because that's the good thing about a high magnetic field, because any local moments are already lined up, right? With 20 Tesla at a tenth of a Kelvin, all the orphan spins are dead, okay? So I think you are probing very intrinsic features. So I expect the phenomenon to just continue. But unfortunately, in your lab, you can go to millikelvin, 10, 20 millikelvin, but not in a high field. So one thing that one might dream of is if someone can cook up another kagome that has just a little bit lower exchange, right? Instead of 50 Kelvin, if it's 40 Kelvin, then it opens up a whole, new world. You can do neutron scattering, you can do, so that's a challenge to the sample growers. Yeah.
All right. So on that challenging note to all the sample growers and others here, I would like to thank our speaker again for a wonderful talk. And thank you for attending the lecture. If there are any remaining questions, please feel free to come to the front.